Hello everyone, welcome to the course Nature and Properties of Materials. In week 7, we'll talk about material selection in engineering design. So this course is offered by Professor Vishak Bhattacharya, Department of Mechanical Engineering, IIT Kanpur. I am your TA for this course, Salka Jankit from IIT Kanpur. So first we'll go through some sample assignment questions which will help you in solving your weekly assignments. Then we'll go through some lecture notes. So first question is, select the material for a circular cross-section cantilever beam loaded at its end having high strength and light weight. Your options are sigma square upon E rho, or under root E divided by rho, or sigma to the power 2 by 3 divided by rho, or sigma to the power 1 by 3 divided by rho. So your answer will be third. So in these questions you have to solve your performance index. So for this you first have to figure out what you have to maximize. So in this case you have to find light weight. So you have to take minimum mass. So you have to write equation for mass. So mass of beam will be your density times the volume. So density is rho and volume will be pi d square L upon 4. So it can also be pi r square L. So now you can write this d square as the other equation as well. So it will be 32 FL upon pi sigma. So here rho is density, d is diameter of beam, L is length. Here F is your applied force, L is length. It is in terms of deflection. So and pi upon sigma, sigma is strength of material. So then you keep all the constants at one side. So it will be pi upon 4 times 32 upon pi to the power 2 by 3. This will be your constant, and length will be L to the power 5 by 3 will be your geometric parameter, and force F to the power 2 by 3, this will be your functional parameter, and rho upon sigma times 2 by 3 will be your material property index. Now this index, in this case mass should be less, so this index you have to minimize, and when you do inverse of this material property index, you will be finding out performance index. So performance index will be maximized. So you have to maximize sigma to the power 2 by 3 upon rho. This will be your PI. So in this diagram bubble chart also you can see that for various materials the plot is for strength versus density. So this is a bubble chart. So in first bubble you have various polymers and foams. In other one you have polymers, you have ceramics, you have metals. So out of these you draw a particular line, and based on that you find out search region. So you have to have high strength. So your material will be having strength higher than this line, and density will be lower in this region. Second question is, which element is most abundant in atmosphere? Okay, so second question is, which element is most abundant in atmosphere? Your options are nitrogen, aluminum, silicon, or oxygen. So we know nitrogen is most abundant in atmosphere, so answer will be nitrogen. So nitrogen is most abundant in atmosphere, and oxygen is most abundant element in Earth's crust and oceans. And from this table also you can see that oxygen is 47 weight% in Earth crust. Highest after that there is silicon, then aluminum, iron. So these silicon, aluminum, iron, calcium, these are abundant, so these don't fall in rare metals. Next up you have in oceans. So in this also 85% is oxygen. So in making up of H2O, you have oxygen and hydrogen. So hydrogen is second one. Weight wise, hydrogen will be lesser. So next up you have in atmosphere, you have nitrogen 79% weight percent, oxygen 19 weight percent, and argon as 2%. Then you have carbon as carbon dioxide, which is 0.04%. Next question is, which of the following strategies cannot be used to encounter the shortage of material? Your options are batch production, continuous type of product, effective utilization of machine, or all of the above. Your answer will be first one, batch production. So batch production is a method of manufacturing where the products are made as a specified groups or amounts within a time frame. A batch can go through a series of steps in a large manufacturing process to make the final desired product. While in case of continuous type of product, an effective utilization of machine helps against shortage of materials. Next question is, for a constant growth rate of 5%, what will be the doubling time TD? The options are 13, 14, 15 or 16. So for this, you have to just use this formula, which is for a constant growth rate of R%, the formula for doubling time TD is given by TD equals to ln2 divided by growth rate. So in terms of log, it will be log 2 divided by log 1 plus R upon 100, which will be which can be approximated as 70 upon R. So R is given here 5%, so 70 upon 5 will be your 14. So this will be the time. Now, which material is less recyclable and eco-friendly? Your options are metal, polymers, ceramic or composites. Answer will be polymers. So polymers, we know that they consist of long chains of carbon and hydrogen atoms, and these molecules form an interatomic type of bonding and is adamant, meaning it is tough for microbes to break the bones and digest them. Thus a long period is required to decompose them, and polymers with hydrolyzable backbones are susceptible to biodegradation under particular conditions. So there are most polymers that I used are not easily biodegradable, so and also single use plastics are also not easily recyclable. So these are these are less eco-friendly and less recyclable, and some biopolymers are also being designed for the sake of environment. Next question is, which diagram is associated with natural resource recovery? The options are Ashby, McKelvey, bubble chart or 2D chart. So answer will be McKelvey. Now these are the McKelvey charts. In this you define various resources according to economy and availability. So McKelvey diagram or McKelvey box is a visual representation used to describe a natural resource such as a mineral or fossil fuel based on the geologic certainty of its presence and its economic potential for recovery. The diagram is used to estimate the uncertainty and risk associated with the availability of a natural resource. And as a geological assurance of a resource occurrence decreases, the risk will increase. And as the economic recoverability of a resource decreases, risk also increases. So from this chart also, there are some identified resources which can be easily mined and easy to recover, and then there are reserves and conditional resources. These are sub-economic, and these ones are recoverable. So there can be some, if we keep on improving the methods to recover them, then these conditional resources, they can also become reserves. Next up, for increasing factor of safety, what should be done? So there's blank, so you have to find out which is correct answer. So your options are diameter or thickness is reduced, impurities are added, diameter and thickness is increased, or heavy material is used. So answer will be, for increasing factor of safety, you have to always increase the cross section. So cross section can be diameter or thickness. So answer will be third. So for increasing the factor of safety, the thickness or diameter of the material is increased, leading to the use of more material than the required. But we use extra material so that the machinery and the design will stay safer for higher time, longer time. Next up, you have which material is not used for making light high performance connecting rods. Your options are magnesium alloys, titanium alloys, aluminum alloys, or zinc alloys. So answer will be zinc alloys. So reason being, zinc and its alloys are not easy to process and are not ductile, and they are not tough, so these are not used for making connecting rods. And the materials for high performance connecting rods, they are magnesium, titanium, beryllium, and aluminum alloys. In case of magnesium alloys, you have AZ61 and related alloys which offer good all-around performance. In case of titanium alloys, you have Ti64, which is the best choice for high F upon L square. And for beryllium alloys, you have the ultimate choice, but difficult to process and very expensive. And aluminum alloys, these are cheaper than titanium or magnesium but have lower performance. Next question is, which materials are abundantly available? Options are copper mercury, silver gold, aluminum iron, or tin tungsten. Answer will be aluminum and iron. So we can explain this by saying copper, silver, tungsten, tin and mercury are rarely available, and as we saw earlier as well, this iron and aluminum, they are available in Earth's crust, so they are easy to mine as well. So these are most widely available materials due to their abundant ores. Next question is, for a household fan, which of the following mechanical property is most important? Options are creep resistance, fatigue strength, sea-water corrosion resistance, or oxidation resistance. So answer will be fatigue strength. So for a household fan, the service temperature doesn't increase more than the room temperature, while creep and oxidation resistant properties are required when the temperature increases above 200 degrees Celsius. And sea-water corrosion is a chemical property and is not required, while fatigue properties are important as cyclic loading is involved in case of this household fan. Now we'll go through some lecture notes. So first you have material selection in engineering design. So mechanical design refers to the mechanical components that have mass, carry loads and other functionalities such as thermal or electromagnetic requirements and must be manufactured. The design refers to the selection of engineering materials based on a set of defined properties, and it is a repetitive process. And this is the design flow chart. So first you have to figure out what market needs, then based on that what is the design requirements, then based on that you come up with a concept in which you determine function structure, seek working principles and evaluate and select concepts. Then you go to embodiment of the concept. In that case you develop a layout, scale and form, model and analyze assemblies and evaluate and select layouts. Then you go to the detailing. In this case you analyze components in detail, optimize performance and cost, and then final choice of material and process is made. Then it is sent to the product specification. Now selection of properties. So first and foremost property is the related to the price and availability of the material. So next up you have density, modulus, damping, yield strength, tensile strength, hardness, fracture toughness, fatigue strength, thermal fatigue resistance, creep strength. These are some mechanical properties. Next you have thermal, optical, magnetic and electrical properties. Then depending on what will be the environment of the final product, it can undergo oxidation, corrosion, friction, abrasion or wear. So these resistance are also required. Ease of manufacturing and joining, etc. For example, cast iron is very easy to cast and use. So in that case we decide which material to choose. Next you have appearance, texture, feel, etc. which come in play in case of polymers and metals. Next you have classes of property affecting product design. So there are various classes of properties. So first is economic and environmental. So in this you will be having price and availability, recyclability, sustainability, carbon emission, that will be related to the material production. In case of mechanical you have modulus, yield and tensile strength, hardness, fracture toughness, fatigue strength, creep strength, damping, etc. Next you have thermal properties. So in this you have thermal conductivity, specific heat, thermal expansion coefficient, etc. In case of general physical property you have density of material. Density also play important roles. So for example you are choosing material for aircrafts or fast moving cars, then you want to reduce the fuel consumption. So in that case you want to consider the density of metals or other materials that are used. Next up you have electrical and magnetic properties. So in this case you have resistivity, dielectric constant and magnetic permeability. So depending on the application these are decided. Environmental interaction. So you want to have material to have high oxidation resistance, corrosion resistance and wear resistance. In case of production you have ease of manufacturing, joining and finishing. For example aluminum alloys, they give good surface finishing and they are easy to manufacture. So according to that they can be chosen depending on what will be the the final product's temperature, service temperature. Aesthetic, in this case you have color, texture and feel of the material. Now why we need to determine the mechanical properties. So for mechanical properties, you first have to run various tests, capture data and analyze and find out what are the various properties of materials. So based on these properties, you design your final component. So based on that, you will design what should be the thickness of your, for example, connecting rod or any cantilever beam, all that, how much material you will be using, will you be using hollow pipe or as a solid pipe. So these all, they are uh, chosen based on the properties of materials, and based on these properties you can decide or choose which material you can take, with also keeping your cost in mind. So if you reduce the amount of material used, then it will become a profitable approach. Next up, you have relative prices of various materials. So here you have used mild steel as 100 as a standard. So relative to that, you the various prices of materials are given. So in case of PVC, you have 300, plywood you have 150, low alloy steels you have 200, almost twice of the mild steel. And mild steel, it's kept 100. Cast iron is cheaper than that, it will be around 90. Soft goods will be 50, and like that, coal will be cheaper, so it will be around 20, and similar to cement. Then in case of platinum, diamond, these are in millions, so it's 12 million. So if you are keeping uh, per ton, the cost per ton, it is relative cost. So copper, these all will also be very expensive compared to mild steel. Next up, you have abundance of elements. So your cost of final material will be mainly based on two factors. First of all, how easily their ores are available for a metal. If, for example, aluminum, bauxite is very easily available, iron, so you have iron ore is also available easily, hematite and magnetite, so these are available easily. So, and other factor is how easily you can recover this ore from that ore. So how much, if you require very less energy, then also it becomes cheaper. So as I told earlier during a question as well, nitrogen is a very abundant in atmosphere, and second is followed by oxygen. And in case of crust and oceans, you have oxygen is most abundant. And because it has your sand mainly consists of silica and alumina, so these silicon and aluminum are also abundant. Next up, you have doubling time. So it is basically a period of time that is required for a quantity to double in size or value. So when the relative growth rate, not the absolute growth rate, is constant, the quantity undergoes exponential growth and has a constant doubling time or period. Example is applied to the population growth, inflation, resource extraction, consumption of goods, compound interest, and volume of tumors. And for a constant growth rate of R%, the formula for the doubling time TD is given by ln2 upon growth rate. And in case of log, you can write log 2 upon log 1 plus R upon 100, which can be approximated as 70 upon R. Resource availability. So in current reserve, it is non-deposits that can be extracted profitably at today's price using today's technology. And resource base is current reserve plus known and unknown deposits. So your reserves will be are the ones which are already have identified ores which are economic to extract. And as you come down to this, okay, as you come down to this part, as you keep on going down here, so it becomes minimum mineable grade, then these resources are not economic to extract. So for this you need to find improved mining technology. And if you move to this side, these are increased prospecting. So here these have undiscovered ores. And so in this side you have decreasing degree of geological certainty, and in this case you have decreasing degree of economic feasibility. And here this is the energy that is required, energy that is consumed to extract these metals. So in case of aluminum, you do it by electrochemical process, so it requires very high energy, around 280 gigajoule per ton, while in case of, for example, steel, it is required less, because in this case you just melt the material, so it is around 55 or so. In case of plastics, you require 85 to 180 gigajoules, and least is for cement and bricks. In case of availability, you have copper, silver, tungsten, tin, mercury. These are rarely available metals. And in case of iron and aluminum, these are the most widely available materials. And steel consumption is doubling in every 20 years, and aluminum consumption is doubling in every 9 years, and polymer in every 4 years. Now, how to encounter shortage of materials? So material efficient design, we can use less amount of material. For example, for a good surface property, we can use cheap substrate and good surface finish. And in case of substitution, you can substitute rarer material by the more available ones. For example, copper can be substituted by aluminum. Next, you have recycling. So we can use recyclable material such as aluminum. And some of the examples of critical minerals which are used in advanced technology, these are solar panels which use arsenic, germanium, indium, tellurium. In case of battery storage, cobalt, graphite, lithium, manganese, these are used. In case of wind turbine, you have aluminum, rare earth elements. In case of national defense, you have chromium, gallium, scandium. In case of aviation, you have niobium, tantalum and vanadium. Now in eco-efficiency, you have it merges ecological and economic goals. So improving the productivity of energy and material inputs to reduce resource consumption and cut pollution per unit of output. It is a win-win approach that benefits both the bottom line and the environment. In 1989, Procter & Gamble introduced concentrated detergent powder, which was called ultra detergents. It took up to half the volume of traditional detergents, and the products cleaned the same amount of clothes but were more convenient for the consumers to handle, and used 30% fewer raw materials required, 30% less packaging, and substantially cut the energy needed to transport them in market. Next, you have 7 dimensions. So these are seven dimensions. So first, to reduce the material intensity of goods and services and reduce the energy intensity of goods and services, reduce toxic dispersion, enhance material recyclability, maximize sustainable use of renewable resources and extend product durability, increase the service intensity of goods and services. So the greater the improvement in each of these dimensions, the more the dimensions and the more eco-efficient a product or a process is. Now these are the Ashby charts, or known as 2D charts. In this case you draw two different properties as two axes. So here density and strength are plotted. So here you find out for various bubbles you find according to the category of materials. For example, you will be finding a ceramics category, polymer category. So all polymers will be having strength very near to particular range and density particular to some range. So then you will be finding out some bubble. So based on these, you draw these guidelines for the minimum mass design. So for example, if you want to reduce certain thing, you want to reduce mass in a racing car, then you draw this guideline, and depending on that you define your search region. In case of 3D chart, you will be having three different properties plotted with three different graphs. So it is performance of a component depending on the combination of various properties. So 3D chart here is of Young's modulus, density and strength. Next you have cantilever design. In this problem statement, you select a cost effective material for a circular cross section cantilever beam loaded at its end, having high stiffness and light weight. And its solution, in this case you have free variables as radius of circular beam, cross section which is diameter equals to 2r, and you also have freedom of choosing material. So the constraint is you have to find maximum deflection and beam length. So tip deflection delta is given as FL cube upon 3EI. Here you have F as force, L is length, E is elastic modulus, I is your moment of inertia. So the end force and the tip deflection can be related. So F equals to 3EI upon L cube delta, and here 3EI upon L cube is the equivalent stiffness. So for a circular cross section, moment of inertia is given as I equal to pi d to the power 4 divided by 64. So here this much is your deflection and this is your length, and force is applied in this direction. So the mass of beam can be given as density times the volume, and your mass becomes equals to rho pi d square L upon 4. Now using equation 1 and 2, we can get d square as equals to 64 FL cube upon 3E pi delta whole square root. Now in terms of mass, you put this value of d square in this formula, so it becomes pi by 4 rho L times this entire d square value. Now you segregate these various properties. So for example, you keep constants at one side, so pi by 4 times 8 upon root 3 by 3 pi, this becomes your constant, and L times L to the power 3 by 2, this becomes your geometric parameter. Under root F upon delta, this becomes your functional parameter, and rho upon root E, this becomes your material property index. So in this case we try to maximize performance index, which is Pi equals to inverse of material property index. So mass we try to reduce, right, in particular property we're trying to find lightweight material. So mass we are reducing, so we are reducing this property. So when we try to in case of performance index, you tell that you are trying to increase this performance index, which will be inverse of material property index. So it will be root E upon rho. Next up you have now maximization of this performance index root E upon rho, which gives us the solution. Now we require some kind of a cutoff value C. So root E upon rho will be equals to C, and taking logarithm on both the sides, we get log E equals to 2 log rho plus 2 log C. Now we get a plot of a log plot of the system, that means log E over log rho. Then depending on this cutoff value C, we actually have a straight line in the log plot, and the material which are below this point are not suitable, and the materials which are above this point, these materials will be suitable for our application. Now here Young's modulus and density are plotted here. So as you can see, this is your guideline, which is contour of E under root E upon rho. So now these materials will be in search region, so these will be suitable. So CFRP is best material in terms of performance, but it is very expensive, hence wood is the best choice among the given materials. Now from this table you can see value of E density and value of E under root E upon rho. Now this is highest for CFRP, but second highest for wood, and its value is very high, cost is very high. Next you have high strength cantilever design. In this case, your problem statement is you have to select a material for a circular cross section cantilever beam loaded at its end, having high strength and lightweight. In the previous slides, we found out the performance index for lightweight and high stiffness beam as Pi equal to root E upon rho. In this case, you have free variable as beam diameter and material choice. Constraint is you want to have maximum deflection and beam length. So here we neglect the self weight of the beam. Now using bending theory, we get sigma equal to md upon 2I. Now bending moment is given as m equal to fl. Now this is your bending moment, and you are applying some force, so there will be tension in one part of your this beam and compression in one part. Now sigma can be given as FLD upon 2 pi d to the power 4 upon 64, and d can be given as 32 FL upon pi sigma times the 1/3. Now mass of the beam can be given as m equal to rho pi d square L upon 4, and now this d square value you can put from this equation, and it will become pi upon 4 rho L times 32 FL upon pi d to the power 2/3. Now you again segregate these constants, so this one becomes constant, L to the power 5/3 becomes your geometric parameter, F to the power 2/3 becomes your functional parameter, rho upon sigma to the power 2/3 becomes your material property index. So its inverse will be your performance index. So Pi will be sigma to the power 2/3 upon rho. Now because for many safe engineering designs, we can at most take the rho P, particularly if it is linear elastic system, etc. So sigma P becomes your yield stress. So up to yielding, you limit your materials. So after yielding, you don't allow that much force to your system. Now maximization of this performance index gives us the solution. Now we require some kind of a cutoff value C. Now this one will be kept equal to C. Now by taking log at the both sides, so log sigma y equals to 3 by 2 log rho plus 3 by 2 log C. Now in this case you have an intercept C and you have a line at particular slope, so above this you will be finding search region. This will be suitable. So in this case you will be having low density and high strength. Now the intercept of the inclined line is adjustable to suit our needs, but the slope is fixed for a particular performance index. So in this case this is your guideline. So above this you have various materials such as silicon carbide, alumina, silicon nitrate. These all materials you can choose. Next problem statement is connecting rods for the high performance engines. So a connecting rod is an engine component that transfers motion from the piston to the crankshaft, and together with the crank they form a simple mechanism that converts reciprocating motion into rotating motion. So you have function as connecting rod, objective to minimize the mass, and constraints is the length is specified. It must not fail by buckling under given force, and it must also not fail by fatigue under the given force. The free variables are material choice, cross sectional area A equal to width times the your how breadth versus width. Now this is the force that you are applying, and this is the these are the your parameters. Now we assume that the shaft has a rectangular cross section A equal to B times W, and here objective function equation becomes M equals to rho AL. Now the fatigue constraint requires that the F upon A is lesser than or equals to sigma E. Sigma E will be your endurance limit, which has stress level below which material will not fail by fatigue for an infinite number of cycles. The material index M1 will be equals to rho upon sigma E, and M2 will be rho upon root E. Now you have two material index, so you can use this equation. So M2 equals to alpha pi square upon 12 times F upon L square whole power half times the M1. So here M1 and M2 are material indexes. Alpha is your shape factor, or you can write this entire bracket thing as a CC, which is coupling constant. F upon L square is your structural loading coefficient. Now drawing coupling lines for two values of F upon L square are plotted taking alpha equal to 0.8. Now these are two coupling lines for F upon L square value as 0.05 MPa and 5 MPa. Now in between these you can find your material. Now beryllium and its alloys, these are in between these, so its alloys emerges as the best choice for the values, all values of Cc within this range. When F upon L square is large, for example when it is 5, the best choice are titanium alloys such as Ti, 6Al and 4P. When F upon L square is small, F upon L square equal to 0.05 MPa, magnesium alloys such as AZ61 offer lighter solutions than aluminum and titanium. Now these are the 4 alloys that are mainly used for high performance connecting roads. So in this case you have magnesium alloys, which are AZ61 alloys and related alloys. They offer good all around performance. Titanium alloys, in this case you have Ti64 is the best choice for high F upon L square. Beryllium alloys, it is the ultimate choice but difficult to process and very expensive. Aluminum alloys, you have these are cheaper than titanium and magnesium but have lower performance. Next up you have design of a probe for scanning probe microscope. In this case it forms image of surface using a physical probe which scans the specimen by feeling or touching the surface with a mechanical probe. So this is your probe, which is a cantilever having a tip. Now it is scanned through the entire surface. So as soon as you find some surface feature, it will be giving you some type of signal and plotting this entire surface morphology. Now the probe is a cantilever beam whose end deflection is detected as a change in the laser beam position at the detector, and the bottom surface of probe has a sharp tip which is 3 to 6 micrometer tall pyramid with a 1540 nanometer end radius. The deflection corresponds to surface topography. Now for this problem statement is, first you have to select a material for the cantilever beam such that the resonating frequency is maximized. In this case you have objective of maximization of resonating frequency so that you can get better signal, and in case you have constraint that you have limited length and thickness to work with. In case of free variable, you can choose whichever material you want. So you have to mainly find out the property index. Based on that you have to find in which area you have to search the material, and you have to realize which material will be best. Now cantilever should have a high resonant frequency, preferably in the range of 30 to 100 kilohertz. Now force between the tip and the sample leads to the deflection of the cantilever according to Hooke's law, which is your stress is equals to strain times the elastic modulus. Now for angular frequency omega n, you can write under root kb upon m effective. M is effective mass, kb is your constant stiffness. So end deflection of a cantilever beam delta is given as FL cube upon 3EI. Now F upon delta can be given as 3EI upon L cube equals to KB, which is stiffness. Effective mass is you count the entire mass of this tip and combine with this beam. So 33 upon 140 times the MB. MB is mass of beam. So MB will be equals to rho L WT. WT will be equals to MB upon rho L. Now frequency can be given as in terms of angular frequency as 1 upon 2 pi times omega. So 1 upon 2 pi times under root kb upon m effective. I is your inertia. So moment of inertia is equals to WT times cube WT cube divided by 12. Now you put all these values in this equation for frequency. So you have to maximize the frequency, right? So you have to find the value of this entire thing. So 1 upon 2 pi. So you put value of kb. Kb you find out that it was in this terms. So you put 3e times WT cube divided by 33 upon 140 times rho L WT times 12 L cube. Now you solve all these equations, then you find this is the constant part, this is the your parameter, this is the material property index. Now this becomes 1.03 divided by 2 pi times the T upon L square times the under root E upon rho. So log E will be equals to log rho plus 2 log C. Here under root E upon rho should be maximized. Now frequency should be maximized, so this should be maximized. Now we choose the material with high ratio of E upon rho times the square root of E upon rho. So your slope will be 45 degree. So in practice, the cantilever is typically made up of silicon nitride Si3N4, which is cheaper, and or diamond with a tip radius of curvature of order of nanometers. Now this is your guideline, and in this area you can find out that you have various ceramics such as diamond and this silicon nitride, silica, alumina, beryllium carbide and CFRP, glass. These all will fall in this search region. Now that's all from my side.